Hello, ladies and gentlemen. Welcome to Physics 20, Kinematics, Lesson 7, Applications of the Acceleration Due to Gravity, Part 1. Today we're going to explain qualitatively and quantitatively uniform and uniformly accelerated motion when provided with the written descriptions and numerical and graphical data. Now, gravity. Who invented gravity? Who discovered gravity? Who was the first to explain gravity? Well, unfortunately we have a little thing to play with here. Now, this is an app showing you velocity and displacement of dropping objects. So if we drop something on Earth, it falls. Yes, not the most exciting lab, but as you notice, similar to our acceleration versus displacement lab, or acceleration lab, you notice we have a curved displacement time graph, which means velocity is constantly changing. And we get a slope on our velocity time graph. From that slope, we can calculate the acceleration. I really hope it's 9.81 meters per second squared. Anyway, now that's on Earth. Now if we're going to go Moon, we can drop it. Now, looking at how slowly it's dropping, you can see it's curved, and the velocity time graph is much less steep, much shallower. And on the other hand, let's look at Jupiter. Now actually Mars is pretty much the same as Earth. Actually, no, it's only about 40% of the gravity of Earth, which is why it doesn't have an atmosphere. Anyway, let's look at Jupiter. There we go. And again, ooh, notice how much steeper the velocity time graph is, and how much more curved, or the distance time graph is curving up much quicker. Right? And notice down here for gravity for Jupiter is 24.79 meters per second squared. Right, not the best simulation, but trying to drop something and record the time, it sucks. Anyway. Now, early Greek natural philosopher Aristotle, 384 to 322 BCE, before our Christian era, made a detailed study of many topics, including gravity. Aristotle theorized that the objects such as rocks and people fell to the earth because that was their natural place. Objects such as birds or paper airplanes acted against gravity because the sky was their natural place. Now this does sound wacky, but this idea was powerful enough to stick around for about 2,000 years. Now, Aristotle used thought experiments to test his ideas. He didn't actually try any of the experiments out, which kind of sucks. Now, one experiment involved dropping two objects, a feather and a rock, through a column of air. According to Aristotle, heavier objects fall faster than light objects. Now, another app for this. Here we have dropping things off the Leaning Tower of Pisa. So, having the atmosphere on, let's drop an iron ball versus a basketball. Drop, and you can see the iron ball is falling faster than the basketball. There we're dealing with air friction. If we get rid of friction, drop it, and they both fall at the same rate. Indeed, iron ball versus feather. If there's no air, they'll fall at the same rate. Now the trouble is, of course, there's air here. And that friction from the air, you notice the feather slowly falling. Yeah. So that friction, actually we haven't talked about that air resistance, slows it down. Since the feather's so light, the air resistance is quite high. Now, as I said, what was that? Yeah. Sorry, lost my train of thought there. So if we dropped two objects, according to Aristotle, the heavier object falls faster than light objects. It's not that they're heavier or lighter, it's the actual air resistance. But we'll deal with that later. Now, it was Galileo. It wasn't until the famed astronomer Galileo Galilei, 1564-1642, hit the scene that notions about gravity changed. But Galileo did more than just study the effects of gravity. He invented the telescope. Really, he would find an idea from James Gregory and improved upon it, and he also invented the Galilean thermometer, that object to the right there. This is density to measure weight, or density to measure temperature. Really quite neat. Now, Galileo performed actual experiments to try to study gravity. However, because the time it took most objects to fall was very fast, the stopwatch had not yet been invented, Galileo had to dilute the force of gravity by using inclined planes, ramps. Where have we seen that before? Now, from these experiments, Galileo concluded that all objects, regardless of the mass, felt the same acceleration. This is called the acceleration due to gravity, g, with a little bar above it, making it a vector. So acceleration due to gravity, g, is minus 9.81 meters per second squared. That's the acceleration due to gravity. Okay? Now, years later, Galileo's theory was confirmed. All objects in a vacuum fell at the same rate, the acceleration due to gravity. Yeah, if you actually want to, you can find the video NASA made on this in dropping a rock and a feather on the moon. There's also ones out there where they used a vacuum tube. Anyway, now, acceleration due to gravity key points. G is a vector, and it's a little arrow above. G can be used in place of A, acceleration, in any kinematics equation. 3, it's actually only minus 9.81 meters per second squared at sea level. More on this later. And 4, minus 9.81 meters per second squared is an exact value and it's not subject to significant digits. It is on your data sheet. Okay? Now, here are some typical questions dealing with objects falling towards the center of the Earth. An apple is dropped from a height of 1.25 meters. A, how long does it take the apple to hit the ground? Well, so first things first, underline or highlight everything important. Height, and it's dropped. So there's the apple falling. So V initial, V final, acceleration, displacement, and time. Now, we're dropping it, so V initial is 0. Now, traditionally, down is negative, so this is minus 1.25 meters. Acceleration is g, which is minus 9.81 meters per second squared. So we can solve for time. Now, we do not have V final, but do we have an equation? We don't have V final. We can solve for time. Yes. Displacement, V initial t plus 1/2 at squared. So minus 1.25 meters. The initial is 0. 1/2 minus 9.81 meters per second squared times time squared. 0.25 meters. 0.9. So 1/2 of minus 9.81 is minus 4.905, I think. Oh, times squared. So divide both sides by minus 4.905 meters per second squared. Time is, I don't know, can't do this in my head anymore. Oh, you poopy head stuff that. 1.25 divided by 4.905. Notice the two minuses cancel out. So that is 0.255 seconds squared. So the time, the square root of that, square root my answer, 0.5. About half a second to fall. Now, 1.25 meters, actually I should go 3 significant digits, so that's 1.505 seconds. Okay? So how long does it take the apple to hit the ground? About half a second. With what velocity was the apple moving just before it hit the ground? That's V final. V initial, V final. Now, you don't have to rewrite this because you've got the data table just above you. I have to because I'm not flipping backwards and forwards. Now, which formula do we use? Well, I don't completely trust the time because there's a chance I made a math boo-boo. So I'm going to use the formula that doesn't have time in it. Velocity final squared equals velocity initial squared plus 2AD. Yes, this will allow us to calculate our final velocities. V final is 0 plus 2 times minus 9.81 meters per second squared, 1.25 meters. And once again, I can't do that in my head. 2 times 9.81 times 1.25. Oh, you poopy head. I'd be like that. Just one sec. So we got Mr. Calculator working, and it's 24.5 meters per second, I think. Now, I'm getting old. You guys, pause the recording, double check my math for me. Sorry about that. Anyway, I think my math is right. At least I hope it is. And there's another part to go with this. Oh, okay. Yeah, let's just do this one. How high will it go? Well, this is part of the question. Well, actually, that's a dumb question, because how high will it go? I'm dropping it. I'm not throwing it up. So, 25 meters. Okay? Now, if I was throwing it up, that'd be something different. All right. Let's pause the recording here. If you've got any questions, shoot me an email. Otherwise, good luck.